As per our tradition, we'll start this program with the university song. So Chetan sir, could you please start the university song? If it's, yeah.
सुन्दरं मन्दिरं शारदाया मुम्बापुरी विश्वविद्यालयम् इदं सुन्दरं मन्दिरं शारदाया मुम्बापुरी विश्वविद्यालयम् कलाशास्त्रवाणिज्यशाखा विरूढा अमूढा विमुक्ता विहङ्गा वयम् शृण्वन्तु सर्वे दृढं निश्चयम् शृण्वन्तु सर्वे दृढं निश्चयम् इदं सुन्दरं मन्दिरं शारदाया मुम्बापुरी विश्वविद्यालयम् सत्यं वदामो धर्मं चरामो नयामो नृणा दुःखभारं लयम् सत्यं वदामो धर्मं चरामो नयामो नृणा दुःखभारं लयम् स्वधारेरतारां सदा जागृतानां भवेत् किं भविष्येति तस्मात् भयम् शृण्वन्तु सर्वे दृढं निश्चयम् शृण्वन्तु सर्वे दृढं निश्चयम् इदं सुन्दरं मन्दिरं शारदाया मुम्बापुरी विश्वविद्यालयम् युवा स्यात् बलिष्ठो युवा स्यात् गरिष्ठो युवा ध्येयनिष्ठो विभूयाद्वयम् युवा स्यात् बलिष्ठो युवा स्यात् गरिष्ठो युवा ध्येयनिष्ठो विभूयाद्वयम् यदि स्यात् युवा राष्ट्रकर्तव्यनिष्ठा समानेर्तत्त्वं विलोकत्रयम् शृण्वन्तु सर्वे दृढं निश्चयम् शृण्वन्तु सर्वे दृढं निश्चयम् इदं सुन्दरं मन्दिरं शारदाया मुम्बापुरी विश्वविद्यालयम् वन्दामहे
you, Chetan sir, and welcome back, all of you. So, today our speaker is Professor K. Sridhar from Tata Institute of Fundamental Research, and it is my pleasure to introduce him today. So, Professor Sridhar did his B.Sc from Wilson College, Mumbai, and his M.Sc and Ph.D from Department of Physics, University of Mumbai. He did his postdoctoral work in Birkbeck College, London, Physical Research Laboratory, Ahmedabad, and Theory Division, CERN, Geneva. After joining TIFR as a faculty member in 1995, he has had visiting appointments in CERN, Geneva, LAPP, Annecy, University of Orsay, Paris, University of Durham, DAMTP, Cambridge, University of Southampton, and IPNL, Lyon. His research is in the area of theoretical high-energy physics, where he has published extensively. He has presented several talks and lectures, both at technical and popular levels. He has published a book on brain worlds and extra dimensions for Cambridge University Press in their series. The Cambridge Monographs on Mathematical Physics and an and also edited volume on integrated education. He has also been involved with UDP quite a lot in present times also. So welcome to you, sir. A very warm welcome, and thank you for taking out your time for us. And I will just pass on the mic to you without delay. So please, you can begin. Thank you very much.
Okay, thank you very much to all of you from UDP for having me over. I hope I'm audible to everyone.
Yes, sir.
Yeah, okay. So I just want to say that in possibly more than the other alumni who have featured in this series of talks, I'm probably someone who is much more an insider to UDP than any of them, because I did not only my M.Sc from 83 to 85 there, but also from 85 to 90 I was there as a PhD student. And so it was 7 years. So both UDP in particular and the University of Mumbai in general meant a lot to me. A lot of what I am now is being shaped because of the university. And I think that is something very important. And if there are students listening to me now, this is something I want to tell them. And that, doing an MSc and especially a research in a university is a great experience because of the fact that a university, by definition, brings a lot of very people from very diverse backgrounds together. And in fact, that was what I benefited from, much to the chagrin of people like Professor Rangwala, who saw me sitting in the canteen with people from sociology and people from economics all the time and not attending my labs when I was supposed to do. But then I wanted to be a theoretical physicist. And at that age, being a theoretical physicist means bunking all your experiments. And I did that very successfully. And uh, luckily there was someone I could copy my journal from, so it was not a problem. No, but yes, Professor Rangwala was always there. He's someone I remember very, very fondly because a lot of the direction that my career has taken from there is thanks to him. I mean, he stood by me, to the rock solid support. He advised me, admonished me when it was necessary, and in fact, it was quite often then. And yeah, so yeah, it's a lot of fondness that I remember him and the others in the department. And of course, as I said, it was not just the physics, but being in the university was also life-altering for me because of the friends I made, people I met, the influences that came into my life, but also the fact that the person who is now my wife, I met her in the university in 83, and uh, we decided to get married just outside the university canteen. in 1989. And so there's a lot I owe to this university. Um, if I have your permission, Anuradha, I just want to start by reading just one small passage from this is my novel, twice written. I hope you can all see it.
We would
Um,
love to hear. We would love to hear you.
yeah, so this is actually about uh, my protagonist Prahlad, who, like me, wants to become a theoretical physicist. Who, like me, goes to University of Mumbai because fancy places like TIFR will not admit him, and who, like me, starts his PhD in UDP. You know. And this passage is about him literally starting his research. So this is about Prahlad. There was a lot happening in his life in those 3 weeks, of which the exam he had to take for his PhD fellowship was the most important. The results were expected only 3 months later, but he had done so well in the exam that Professor Chitre felt he need not wait for the results, but could start studying some of the more advanced topics he needed for his PhD. After the formality of a departmental interview was completed, Prahlad was admitted as a student and given a desk and a shelf in the student's room. He felt overwhelmed the day he went and occupied the desk. It hardly mattered that it was an old desk with layers of dust on it. It had not been touched for years, it appeared. He wiped the desk clean with a wet mop and proceeded to clean the shelf and the windowsill next to it. It took him some time to clean the drawers. He was told he could just chuck all the old papers that it contained. It had belonged to students who had left the department a long time ago. There were letters, official and personal, from the university granting extension of the PhD term or accepting a thesis synopsis submission, from conference organizers with impersonal letters of invitation, from journal referees trashing a paper completely, saying the calculations presented in the paper had several obvious flaws and the paper was totally unsuitable for publication, from family asking about their son's progress and reminding him that his sister's wedding was not far off, from a fiancé or a lover, it wasn't too clear, talking in the same breath about the impending life changing decisions that needed to be made and the purchase of 2 new saris. Other than these, there were several bills, a 14-year-old one for the purchase of a table fan, another 19-year-old hostel mess bill, and many more, some possibly unpaid. There were bank papers, check deposit stubs, postcards with Ajanta Ellora frescoes, an empty packet of Navy cut cigarettes flattened out for so many years that it could not be pulled back into its original shape. What Prahlad was pulling out of the drawers was, in fact, an eloquent narrative of the trials, tribulations, frustrations, and the moments of joy that was typical of a PhD student's life. When, having cleared the drawers, he put in photographs of Kamla and Laila there, he was starting a new chapter of this narrative. Thank you. Okay, I'll start with my talk for today. Let me just get that going. Oh God, I'm not being able to share screen. Can someone enable it, please?
Chetan sir, can you see? Chetan sir, can you make him the host?
Yeah.
Yes. Now he can.
Now he can share.
No.
Okay. I think we're all right now.
Yes.
Yeah.
Yeah.
Okay. So I'm going to be talking today about um, my area of research, which is high energy physics. And when I say that, I remember a friend of mine who told me that I shouldn't be telling people that I work in high energy physics because they'll end up thinking that I work on a hydroelectric project on a dam or something. And it's of course also difficult to tell people that you work in elementary particle physics because they won't understand whether elementary applies to particles or whether it applies to physics. And they would probably be wondering why you're not doing advanced particle physics instead. Okay, having said that, um, the subject, which is either called high energy physics or particle physics, this is my area of research. And the title of my talk today, Where Do We Come From? What Are We? Where Are We Going? This is actually a very evocative title that I chose for this talk because it sums the kind of fundamental questions that the subject asks, but it is also the title of a very, very famous painting made by Paul Gauguin. Um, Sorry, there is some issue. Can just 1 minute? I'll see what's happening. No idea what's happening.
Try to use keyboard.
No, I seem to just. Can we stop for a moment, please? I'll just.
Yeah.
Okay. I think we're okay now.
Yes.
Yeah. Okay, so this is the painting that Paul Gauguin made, which was from his days in Tahiti. And this painting is in fact titled exactly what my talk is titled. And Gauguin was, as many of you probably know, uh, artist committed to the idea of primitivism. And he was choosing to work with primitive forms, but he was also choosing to ask primitive, that is, very fundamental questions. And so this title is really asking questions about our origins and structure. Where did we come from and what are we? And eventually where we are going. So this is roughly the kind of map this talk is going to take. the kind of path that this talk is going to take. And um, sorry, there's some noise in the background. Can you mute your microphones, please? Yeah.
Everybody is requested to
So,
please keep your videos and audios off. Yes, sir. Please continue.
yes, so um, I'm going to be talking about essentially the structure of matter, which is what the subject matter of particle physics is. But that question is intimately tied up to the question of origins. And this is a very important thing to realize. And so that's what I'm going to start with right now. Again, I'm not being able to move forward. There's something wrong with the screen sharing.
You can check on the top screen. If some
Sorry?
option on your screen on top view, you just check whether some annotation is enabled or disabled. Maybe if it is enabled, it is not allowing mouse to operate.
No, it's not allowing me to operate. I'm not using a mouse. I'm just using keys.
Okay. So no, because all the controls are with you now, sir.
No.
Sridhar, are you using a PDF file?
No.
Then it should work.
Yeah, sure.
Invite someone else to play the
Should I send it
presentation.
to? Should I send it to you? Then can you play it
Okay.
from there?
Yeah.
Okay, sir. Whom should I send it to? Another to you?
You send it to me, I'll forward it. Yeah. Can you send it to my official email, misra@physics?
Okay. Okay, I sent it.
So yeah, I got it. I'm just opening it. Chetan, can you make me the host? I'm just forwarding it to you.
Fiona, don't do it.
Ritika, are you a host?
Yes, I'm a host, ma'am. You can forward it to me also.
Okay, I'll forward because I'm not a host. So.
Now you are a host, madam. Chetan sir
Okay.
has made you a host.
Okay. Ritika, I'm forwarding it to you. Okay.
Okay.
I'm not able to share.
Okay. Yeah, I have received it. I'll just share my screen. It's opening. Is it visible?
Yeah. Right.
Okay. So
At the
I'll
bottom.
just
Right. Yeah, right there. Previous page, I think.
yes. Yeah. So you can start. You can begin, please.
Okay, we can go to the next slide.
Yeah.
Yeah. So I was saying that the question of structure and question of origin is very intimately tied up in modern physics, and the reason for this is that it has been empirically established that the universe is expanding. So galaxies are moving further and further away. This universe is getting bigger, and that means, in fact, as we go back in time, the universe was smaller in size, and in much earlier epochs, very much smaller. So the amount of energy contained, of course, is the same inside. So the energy densities and therefore the temperatures um, in the early epochs of the universe was much, much higher than what we experience now, which basically means that the universe was very um, hot at early epochs, and that means that matter could not quite exist in the form that it exists now. Structures could not exist in the form that it exists now. Okay. So as we go back in time to earlier epochs in the universe, we see, for example, that matter splits up into its constituents, molecules and atoms and so on. After a certain point, the universe gets hotter, even atoms cannot exist, and it splits up into its constituents, the proton, the neutron, and the electron, and so on. So as we go further and further back in time, I mean, just to give you an idea, I don't know if you can read the time scale on this picture, but um, right on top is where we are now, the present epoch, and that's uh, some 14 billion years right now. And as we go back in time, if you go to very, very early epochs, which means literally a fraction of a very, very tiny fraction of a second after the universe emerged in what is called a Big Bang, at that time, the constituents of the universe, what constituted the universe at that time, are these elementary particles, which we are now studying in the laboratories, in high energy laboratories. So um, it is actually a very, very intimate tie-up between how the universe originated. So what we will further study in laboratories at higher energies will take us closer and closer to the very origin of the universe. Okay. Next slide, please. Can we go to the next slide?
Yeah, I'm trying, but it's not going somehow. I think there's some issue. The same problem I think you were having.
Yeah. Uh,
It's showing it's processing something. Let's see.
Someone suggested I can show in the edit mode itself instead of trying to do a slideshow. Can I do that?
Yeah. Yes, sir. That
Yeah, that
maybe
would be
because
better.
too much, I
Uh,
think a lot of pictures and things are there. So it may be the case. So
okay, let me try that.
should I stop sharing?
Yeah. Can everyone see this now?
Yes, sir. Yes, sir. I
Okay.
think this is better.
Okay, so it's going to look a little ugly, but sorry, I cannot help it. I had one apology already planned, which because of this confusion, I forgot to say. But now I should, in fact, instead of one, I should offer two apologies. The first apology is sorry for this tech mess up. I should have taken care of this much earlier. But I also want to apologize to any of the experts in the audience or all the physicists in the audience, in fact, because this talk is going to be really a very um, elementary talk. I use it guardedly, this word. And it's a kind of talk that I planned, which I hoped it would be accessible to people beyond physics. So, yeah. So let me start with the beginning. So as I said, we're going back in time, we were going back to really the fundamental constituents of which this universe is constituted. And this idea that the universe is made up of fundamental tiny constituents, which is the idea of atomism, is a very old idea. It's probably an idea that has endured the longest in the history of humankind. It's at least 2.5 millennia old. And it originated around 5th century BC, which is my current obsession, of course. And the idea of atomism is, as we said, it's that all matter is made up of small indestructible units, and these units are eternal. And, they continue to be eternally. We should understand the context when the Greek philosophers Leucippus and Democritus came up with the idea of atomism in the context of Western philosophy. We should understand the context in which it was originally suggested, because at that time, the big debate was between Parmenides and Heraclitus. Parmenides was suggesting that the world is what it always was, that the reality of this world is eternal and constant and nothing changes ever in that reality. And Heraclitus, on the other hand, was famous for saying that you cannot step into the same river twice. He was, in fact, saying that the universe is in a constant state of flux, that things are always changing, and there is no one thing that is ever constant in this universe. So actually, the atomists of Greece came up with the idea of atomism. It was a brilliant dialectical resolution of these two contradictory positions of being and becoming, being of Parmenides and becoming of Heraclitus. And they suggested that, in fact, there is a substratum of atoms. These atoms continue to exist forever. They are eternal. They are like the world of Parmenides. But these atoms form composites, and through forming these composites give rise to the phenomenal world, and the phenomenal world is always changing, it's in a state of flux and so on. So this tension between the being and becoming debate in Western philosophy is beautifully resolved by atomism. It also addresses one of human beings' very primal fears, the fear of death, because in an atomistic kind of understanding, there is no death. Everything goes back to its atoms. Atoms are eternal. So we continue to exist in some form, if that gives us any consolation whatsoever. Okay. But just like the Greeks, here in our own country, there was a very, very lively and active tradition of atomism. The Ajivikas were the first atomists in our recorded traditions. And the Jains and Vaisheshikas also took these ideas forward in very interesting ways. The Jains in particular also talked about atoms of feelings and atoms of emotions and so on. This is quite interesting today if you think of it from the perspective of neuroscience. And I just wanted to also mention that this ideas continue to exist much later, about 1,500 years later after these people. Al-Ghazali, the famous Asharite, he was still committed to the idea of atoms in a very, very important and interesting way. Okay. I'll go forward to discuss how this idea of atoms eventually enters physics, for example. But Before I do that, I just want to take a small detour and talk about two important things that happened in between. Okay, because we left the story with some 2,500 years ago, and in between, of course, Newton happened. Okay. We know that a lot of what we call modern physics started with Newton, and particularly because of his precise formulation of the laws of motion. Okay, very clear understanding of what motion is. And actually, Newton's formulation of the laws of motion was uh, putting in place mathematically what Descartes had suggested already, the idea of mechanical causality. The idea of mechanical causality being that when a, when a system, when a body moves or when a object moves, it moves from one state to another, sensing the forces around it instantaneously and moves to the next neighboring point. The entire trajectory of the motion is not known initially. The body simply reacts instantaneously to forces acting on it and reaches the final point. So when we look at trajectories, there's always a confusion about how did, so for example, when a bowler releases a ball in a cricket match, how does the ball know where to land? Did the ball know already that it should land there? And these are the kind of absurd questions that can come up if you think of trajectories instead of thinking of instantaneous um, infinitesimal motions that add up to give the whole trajectory. Okay. So important thing about Newton's laws of motion, which you all have encountered, and I won't actually uh, sit and now enumerate them, but we also know that because he could understand his mechanics clearly, he could then formulate his ideas of gravity. And the important point there is to realize that Newton realized whatever is terrestrial gravity, which means whatever pulls the apples to the earth, is the same that keeps the planets in the orbit around the sun. So the terrestrial and celestial gravity were one and the same. And this was one important um, realization that Newton had. So um, Newton, of course, didn't stop at doing this. His contributions were tremendous. And in fact, he spent most of his time not doing physics or mathematics. He of course, made important contributions to calculus, but he was also an alchemist. And he devoted a good part of his time to alchemy, to theology. He was the master of the mint in England and so on. But one of his physics interests, other than gravity, was optics. He made very important contributions to the study of optics. But because he had already set his mechanics in place, and mechanics is mechanics of particles, the motion of particles. I'll come very soon to discussing what I mean by particles. Newton thought of light itself as made up of particles or corpuscles. And if you think of simple phenomena of light in optics like reflection or even refraction, it is possible to push this idea of particles to explain these. So Newton was initially convinced that they are particles, and later he was prejudiced that they are, and he refused to budge from a corpuscular understanding of light. And here I had this quote from Alexander Pope, which where in a celebratory way he says, "Nature and nature's laws lay hid in night. God said, let Newton be, and all was light." Newton, of course, was worthy of that kind of praise, but all was light was probably the most difficult part, because in his theorizing about light, probably Newton was as far from the target as one could be. Okay, I'll not get into it's a very fascinating history of his fight with people like Huygens on uh, light, and but I don't have the time to discuss it now. People who want to read it should go and read these. They're excellent books on it. But after Newton, the great moment in physics happened with Maxwell. This was in the middle of the 19th century. It was, in fact, around 1864. The Scottish physicist James Clerk Maxwell took up the challenge of understanding the new phenomena of electricity. Electricity had just been um, discovered. People were doing a lot of interesting work with electricity. People like Faraday had found a lot of empirical information about electricity. Magnetism was another phenomenon that was interesting, though it had people had known about magnetism for a much longer time. And at first sight, electricity and magnetism don't look like each other at all. In fact, they look as different as can be. Electricity is something we see running in wires. On the other hand, magnetism is something very specific to certain kind of materials. So what could the connection between the two be? We know, for example, in a cycle dynamo that a coil, you can induce an electric current in it because of a changing magnetic field. The magnet rotates inside the dynamo and produces electricity. It's also true that when you have a varying electric field, you can get magnetic attraction, time varying electric field. And Maxwell essentially tried to put these together. And he said if a time varying electric field can produce a magnetic field and vice versa. So if you have both time varying, then is it possible that these electric and magnetic fields can become independent of the material, sustain each other because of their time variation, and propagate through space as a wave, independent of any material? This was in fact possible. This was his discovery of electromagnetic waves. So in one fell swoop, Maxwell brought together electricity, magnetism, but also optics, because he discovered that these electromagnetic waves travel in space, free space with the speed of light. So he identified them with light, and so he could actually understand all of this in one unified framework. Okay. This is a huge contribution, the first genuinely unified theory of in physics that we have. For people who are not familiar with this electromagnetic spectrum, I'm just quickly flashing this slide. Um, you have to understand that when we say light, this visible light that we talk about, which is from the red to the violet, is only a very, very small part of what we call the electromagnetic spectrum. There are other frequencies in which the electromagnetic spectrum emits, and that is in X-ray, gamma ray, ultraviolet rays at the higher energy end, and infrared and radio waves and so on at the low frequency, low energy end. Okay. So we go back to our story of atomism after this detour. In fact, I said the idea of atomism was widespread in the ancient world, but even those philosophers who did not subscribe to that idea, they actually subscribe to the idea of elements. So the difference being that atoms were something which were not given to perception, that they were substratum hidden from observation, but elements were physically available to the senses. So the ancient world enumerated 4 or 5 such elements, which was like earth, water, fire, air, and sky, depending on whether you include a fifth one or not. And there was also some interesting symmetry between the 5 senses and these 5 elements and so on, which people wrote extensively about. But this idea that these elements combine to form all the substances of nature was an important idea, and it persisted through history, and actually was experimented very much with in the days of alchemy. Alchemy, people now think of as a faith subject, but the amount of work that went into alchemy actually went in clarifying much of what became, clarifying notions of what these elements were, what substances combine with what substances in what ways, which actually paved the way for modern chemistry. So even though alchemy as a subject was discarded, again, much of modern chemistry owes its existence to alchemy. And we know the story of chemistry from there. We know that uh, elements were rediscovered in chemistry, but not the elements that people originally identified as, not fire and water and earth, but the substances, the elements which chemistry identified. There were about 100 of them. And in fact, water was not an element, but hydrogen and oxygen were, and molecules of hydrogen could combine with oxygen in a way to form water. So water was a composite object, whereas these were the elements which went into making water. Okay. So the periodic table that came with Mendeleev, which coded all these regularities of the elements, the properties of elements, and put them together, actually then set up the path to move towards an understanding of the elements in terms of more fundamental objects, which are the atoms of modern physics. So I'm showing you a picture here of a carbon atom, which you have most likely seen. The carbon atom has a structure like this. It has protons and neutrons, positively charged objects, protons, and neutral objects called neutrons in the center of the in center called the nucleus. And in orbits around it, it has these negatively charged particles called the electrons. Okay. Now, I just showed you a picture of the carbon atom, but if you look at the hydrogen atom, for example, you simply have one single proton and one electron. And depending on number of electrons you have and number of protons you have in, you get different substances. So oxygen has 8 electrons and so on. Okay. So the differences between different elements that chemistry identified is now reduced to the number of electrons. It reduced to a quantity. The number of electrons determines the differences between elements. And it's quite important to understand this, that lead and gold now, the alchemist's famous dream of transmuting lead and gold, is actually in a way sidestepped because of the fact that lead and gold are not that dissimilar anymore. Just the number of electrons in their orbit that that discriminates between them. The problem with this picture is that if you combine what you had with Newton and if you had with Maxwell, then this picture seems obviously wrong, because Maxwell would tell you that this electron here is a charged particle. It is orbiting around, it's moving around. As it moves around, it will lose energy by emitting electromagnetic radiation, and it will fall into the nucleus. So if you have an atom like this, it is not going to be stable. Let me remind you again that the electron is being attracted by the protons here, which are positive objects. So in electricity, we know that positive and negative charges attract each other. So from the point of view of the stability of the atom, this is no good. This picture is no good. And that is when people realized, after a lot of deliberation, that a fundamental change in the understanding of mechanics is required. This is not surprising at all, because Newton had abstracted his mechanics by looking at objects which we encounter in day-to-day life. And he had formulated the laws of mechanics. The hope was this mechanics would hold true for really small objects as it did for the planetary orbit. But these small objects are really very small. So to think of it, if you want to get a picture of the size of the atom, think of the smallest division on your ruler, which is millimeter, and then this thing is some, what, 10 million, 1/10 millionth of that. So if you take one small division on your ruler and divide it into 10 million parts, that is essentially the size of the atom. And if you take that and then divide it further by another 100,000, then you get the size of the nucleus. So this is how tiny these objects are. And there is no reason at all that the mechanics that we develop by looking at objects which are macroscopic should apply to this. In fact, the mechanics of Newton was superseded. We know about that great revolution, and we know about how quantum mechanics came to be because of this. Okay. And the famous thing that we all know about quantum mechanics is this question whether these electrons are particles or waves. Okay. I drew this picture pretending that these electrons are particles, but there were already experimental results to suggest that the electron was in fact had wave-like properties. Okay. Now, really, this is the time to understand what exactly I mean by a particle and what I mean by a wave. And for me, the simplest way to think about it is to say that a particle, I talk of anything as a particle if I can ask the question, where is it? And if you can point out to me and say, there it is. So if something can be pointed out to and localized in that fashion, then I would call it a particle. Okay, and this, of course, depends on the dimensions of the problems involved. So if I'm pointing out to a chair doesn't look quite a particle. It's not at one single point, but it is an extended object. But for all practical purposes, if I'm standing far enough from the chair, I can point out to the chair and say, there it is. Okay. An ant on the chair will not be able to quite describe it quite the same way. Similarly, I can point out to the moon and say it's a particle because it is at some given point, and I'm looking at it from a huge distance. A wave, on the other hand, or a field, which we talked of electric and magnetic fields, a field or a wave is something that does not give you an unambiguous answer to this question, where is it? So for example, think of the simplest possible wave. Tie a string to a wall on one end, and from the other end, just shake the string. You set up patterns of wave motion on the string. Now, if you ask, where is the wave? That doesn't make sense because along the dimension of the string, along this length of the string, the wave is everywhere. The peaks and valleys, the crests and troughs, all put together is what we call a wave. So it does not make sense to ask the question, where is the wave? It's all of it. Okay. So while physicists, theoretical physicists are thought of as very creative people, in fact, their creativity is actually quite limited. So they work with very simple models. And these are two different models of reality they work with. One is a particle and the other is a wave. Okay. Now this electron is another kind of beast. It's something which transcends both these descriptions. It's neither a particle nor a wave. It's in fact some described by some mathematical function in a complicated theory called quantum theory. To assume that our naive descriptions of it in terms of particle or wave will actually make sense is is just expecting too much, and that's exactly what happened. These simplistic descriptions broke down, and in fact, Newton's mechanics was superseded by quantum mechanics. The heart of quantum mechanics was what was called the uncertainty principle, which again, I'm sure you have all heard of. And to put it in a literally a couple of lines, Newton's mechanics required that in order to specify any motion, you had to specify the initial position of the object and with what speed it is moving and what direction it is moving. This had to be specified. So the speed and direction combined together in physics is called uh, velocity or momentum. So you have to define the momentum of the particle and the initial position of the particle in order to predict the entire motion of the particle. So in other words, Newton's statement was, give me the initial position of the particle, give me its initial momentum, tell me the forces that are acting on it, and I'll predict its trajectory forever and forever. Okay. Very audacious, but that is true. In quantum mechanics, in fact, you can do that kind of prediction. So quantum mechanics is still mechanistic. So this prediction is still possible, except that the initial state, you cannot specify the initial momentum and initial position as accurately as you want. Because if you try to specify the initial position of this object very sharply, you lose information on the momentum. So these two become complementary kind of variables, and you can't specify both of them to unlimited accuracy. So this, in a nutshell, is what the uncertainty principle is about. And this is exactly what explains, let me go back to that, explains the stability of the atom. Because if the electron were to fall here and sit on top of the proton, then you will be violating the uncertainty principle, because you know where it is on the sitting on the proton, and you know that it has no momentum, it's sitting there at rest. And because of the uncertainty principle, the moment the electron tries to fall in, what will happen is its momentum components will start reacting wildly. It will pick up momentum and it will get pushed back. And in pushing back, it will optimize and find this orbit as its solution. Okay. Okay. The other great revolution we also know about is relativity. Um, this also happened around the same, a little before quantum mechanics happened. And the ideas of relativity came about because people realized that Newton's mechanics, there will be another kind of departure from Newton's mechanics, because it was found out that light, first of all, speed of light is finite. Of course, it's very large, but it's not infinite. It's not that light travels at infinite speed. It's a very large speed. It travels at a speed of 3 lakh kilometers a second, but that's still a finite speed. It takes, in 1 second, it travels 3 lakh kilometers. So in fact, in 1 second, it travels the distance from here to the moon. But what interestingly people discovered, two American experimentalists in the late 19th century discovered, is that the speed of light remains the same in all frames. What does this mean? Okay, go back to Newton's mechanics. If I'm, driving at a speed of 60 kilometers an hour, and John Abraham goes by on his mobike at a speed of 150 kilometers an hour, I'll see John Abraham going past me. If he's going in the same direction as me, I'll see him go past me at a speed of 90 kilometers an hour. It's only the difference that I will see. Okay. Or to put it differently, anyone who has traveled in Mumbai locals understands this very, very intuitively. If you have to get out of a running train, which you always do to impress people around you, then before the train actually stops at the platform, if you're jumping out of the train, what you do is you get out, but you still keep moving till such point that, because the moment you hit the ground, your feet come to a rest. So in fact, you lean backwards and you get pushed forward. Okay. So this relativity of speeds is very important. So you would expect that if I were take, if light travels at a speed of 3 lakh kilometers an hour, and if I were to travel at a speed of 1 kilometer an hour in a direction opposite to that of light, then I would see this light traveling at 3 lakh plus 1 kilometer per second. Um, but that, in fact, turns out to be not true. No matter how you move with respect to the light always moves at 3 lakh kilometers, and nothing can actually move faster than this speed. This is the limiting speed. So when you put all these facts together, you find that Newtonian addition of velocities or subtraction of velocities cannot work anymore. You have to change that. So Newton's mechanics need to be changed. That revision was called special relativity. Okay. Of course, this also means that you'll have to change gravity. Why is that? Because, you know, yes, light, which is electromagnetism, if you have to tinker with that, you also need to tinker with the gravitational interaction. Imagine, for example, that a star that you're observing just to disappear at this very moment. Okay, if it were to disappear at this moment, because light travels at this finite speed, you're going to get information about the speed of about the disappearance of the star only after a little time lag, because it will take that much time for the light from the last light from the star to reach you. Right? But if gravitational interaction were not subjected to the principle of relativity, it was then the effect of gravitational interaction would travel immediately to you. And just from that, you would know that star has disappeared. And that cannot be, because the principle of relativity is that this is the limiting speed. No other communication can happen at a speed greater than that. And therefore, you subject gravity also to the principle of relativity. And when you make it compatible with relativity, a new form of gravitational theory emerges, and that is called general relativity. I'll not go into more detail about this. I've already spent a lot of time in giving this background. So let me now come back again to my story of atomism. As I said, the stability of the atom is one thing that immediately hits you as you see this picture, but that was solved by quantum mechanics. Once that was solved by quantum mechanics, you might have thought that, okay, this is great. We now know that the atom is made up of protons, neutrons, and electrons. There is the electromagnetic interaction, and there is also a gravitational interaction, which Newton or Einstein told us about. And this is the world. I mean, this universe is very, very simple. There are three kinds of particles which make up the world, and they are held together by electromagnetic interaction. And these objects sometimes interact also by gravitational interaction. This would have been the best possible world, to paraphrase Leibniz. But unfortunately, even just looking at the school book picture of the atom, you realize that this is not true. The reason this is not true is right here in the center is the nucleus. And the nucleus, as I told you, is made up of positively charged objects um, called protons and the neutral objects called neutrons. Then the question is, what holds the nucleus together? Because like charges in electromagnetism repel each other. So these protons will not stay there confined to that small space. They'll just fly off. And there's nothing to hold the neutrons anyway because they're neutral. So there must be some force much, much stronger than the force of electromagnetism that overcomes the repulsion of the electromagnetism and holds this nucleus together. Okay. So this means that already by just staring at this picture, you're opening up new realms, which is where nuclear and particle physics start coming into play. So it was this Japanese physicist called Hideki Yukawa, who proposed actually that there is a very strong interaction in the nucleus which holds the nucleus together. Others also said this, but Yukawa said that the origin of the strong interactions is actually due to the exchange of these particles. These are particles that bind the nucleus together, and these are new particles called pions. Very nice. These pions account for the strong forces that hold the nucleus together. And these are um, analogous to, I probably miss saying that in the case of electromagnetism, which I'll repeat later anyway. These are analogous to particles of light, which are photon, which being exchanged between charged particles, which gives rise to electromagnetism. Okay. So this is a nice solution for understanding how strong forces came to be, but this comes at a price. You are paying the price of introducing a new particle. So you were saying you had 3 elementary particles, but now you have to unfortunately bring in a 4th one. Okay. But life was not so easy. It became even worse because people noticed that uh, there is a phenomenon called nuclear decay, which means nuclei can transmute and change into other nuclei. So, for example, in this picture here, a nuclei of cobalt, which is called cobalt 60 because it has 27 protons and 33 neutrons, changes into nickel 60, where one of the protons, um, one of the neutrons from the cobalt gets um, transformed into a proton, and this in this process you have basically created one positive extra charge. To compensate for that, you have to emit an electron. So this um, negative charge that you emit, that is what you see, and these things were called beta decay in the original days, but this um, interaction is called the weak interaction of the nucleus. It's different from the kind of interaction that holds the nucleus together, which is the strong interaction. And this difference is understood by actually measuring the time scales involved in these different processes and realizing that the time scales involved in the strong process are much, much different from those involved in these weak processes. Okay, so the bottom line is there are 2 new kinds of nuclear interactions. So our world is, which was simple, which had only electromagnetism and gravity to begin with, now has 2 more nuclear interactions. Fortunately, these nuclear interactions happen to act only within the size of the nucleus. They only within the nucleus these ranges, these interactions matter. Outside that, it does not act. Okay. And in this reaction, when people studied these reactions carefully, they found that it was impossible to understand the conservation of energy in this, because what energy you put in, that is what you have to get out in these processes. And more importantly, also the quantity called angular momentum. So conservation of these um, quantities could not be accounted for in such process initially. And that is when it was suggested by the Swiss German physicist Pauli that there are invisible particles called neutrinos. These are very weakly interacting particles. They have no charge, so they don't have electromagnetism. They don't take part in strong interactions. So they have no interaction except this weak interaction. And these weakly interacting neutral particles just disappear, taking away energy. And that is what accounts for the missing energy. So life has got even more complicated. We introduced a pion now. Now a neutrino has also come in. And so people started doing experiments to look for the pion. This was starting from the late 30s. People started doing experiments to look for the pions. And these experiments yielded another unexpected result. In the course of searching for pions, they discovered a new particle, which was not the pion. It was, in fact, a fat brother of the electron. It was exactly like the electron, a negatively charged particle, but it was much heavier than the electron. So initially it was mistaken for the pion, but later they realized that this particle, they eventually called it a muon. It was totally unlike the pion. The pion was eventually discovered in the late 40s by English physicist called Cecil Powell, and he and his collaborator shared the Nobel Prize for it. But unfortunately, the person who missed out on the Nobel Prize was an Indian physicist, a woman called Viva Chaudhary, who did the same experiments sitting here in Darjeeling, and she just could not actually confirm that it was a pion as strongly as Powell could do, because these were experiments done with recording the events on photo emulsion tracks. And because of the wartime, she could not get good enough photo emulsion. She was working with half-tone emulsions, and her resolution was very poor. So she could not confirm it and missed out on Nobel Prize because of not having the proper photographic paper, which is a really, really sad story. Anyway, so our world has already got complicated. We have a muon, we have a pion, we have a neutrino. So the world of elementary particles suddenly starts getting busy. And by the end of the 50s or early 60s, it got totally messy because people had started by then doing what are called cosmic ray experiments. Cosmic rays are rays of some unknown origin coming from the deep interiors of stars, and they come and they bombard the Earth's atmosphere. We are being bombarded by cosmic rays at a frequency of something like once in every 2 or 3 minutes. These rays come in, and when they come into the Earth's atmosphere, because they have a lot of energy, they produce a shower of particles. Okay, so this is a very cheap way to do high energy physics experiments because you have these high energy rays that nature is giving you. So all you need to do is sit comfortably on the surface of the earth with your detectors and wait for the heavens to shower, literally. Okay? And when the heavens showered in the late 50s and early 60s, they showered, जैसे कहते हैं ऊपर वाला देता है तो छप्पर फाड़ के देता है. So by the early 60s, people had identified in these cosmic ray experiments something like 100 particles. Yeah. And it became really embarrassing because physicists were being snooty about the fact that chemistry had identified 100 elements and how they had reduced all of that complexity of chemistry to the beauty of a simple atom with just 3 fundamental particles. And now these same physicists were staring at a situation much alike chemistry, where they are now talking of 100 elementary particles. Of course, not all these particles were stable, they were unstable particles. So by unstable, I mean they would live for a short time and then convert into other particles, as you can see in this picture. But all the same, it was a problem understanding why, if these are elementary particles, why there should be these many of them. And this is where another big step, which was essentially the beginning of the subject called particle physics, happened. And that was the understanding that these different 100 particles, along with the proton and neutron, are not elementary. They are in fact made up of even smaller particles, which are called quarks. You can see on this right-hand side of the picture, these blue dots, these are quarks. Now we have, in fact, initially people had proposed a scheme with just 3 quarks, which was enough to account for all these particles that had originally been discovered. But then that number has gone up to 6. So we have 6 objects which are called quarks, which go on to make up particles, the strongly interacting particles like protons and neutrons, and all these different 100 particles that I was talking to you about. In addition, you have these 6 golden particles here, which you can see on this side, which are these 3 are all like the electron, the muon, and even fatter cousin of the electron called the tau. Okay. And each of them has a neutrino associated with it. So there's a neutrino for each such charged object. And so you have 6 of these kind. These are collectively called leptons, and 6 quarks. So 6 quarks and 6 leptons, that kind of completes the entire picture for the understanding of subatomic world. The sizes of these different quarks and leptons here actually reflect the sizes, reflect the variation in the masses. So Some of these are very light, as you can see, they are small, and some of them are very big and they are heavy. And more importantly, there's a very fundamental theorem from the theoretical point of view, which says that if you have 6 of these objects here, you need to have 6 of these here. So in fact, when I started off as a PhD student in the late 80s, this sixth object here, the top quark, was not yet discovered. That was discovered only as late as 1995. So there were 5 quarks and 6 leptons, but we all kind of expected and knew that there would be a 6th quark because of this fundamental theorem which says that if you have 6 objects on this side, there ought to be 6 on this side. Otherwise, your whole theory is inconsistent. So the 6 and 6, these 12 particles, and 4 interactions, as I already have explained to you. The 4 interactions are the electromagnetic interaction, the gravitational interaction, the strong nuclear interaction, and the weak nuclear interaction. Okay. And these interactions are mediated in the picture that I'm going to talk to you about by particles themselves. Okay. And these particles the electromagnetic interaction, for example, is mediated by particles called photons. The um, strong interactions are mediated by particles which are called gluons. So the gluons are exchanged between these quarks to give rise to the strong interactions that we see inside the nucleus. The weak interactions which are responsible for the beta decay that I talked about are mediated by 3 kinds of particles. They are called W plus, W minus, and Z. And gravity, least understood, and that is expected to be mediated by gravitons, but these have not yet been understood. Picture is now like this. We have 4 interactions and 12 particles. These 4 interactions, strong, electromagnetic, weak, and gravitational, I have put them in the descending order of their strengths. So if strong interactions are in the range of 1 to 10, it's a dimensionless number. The strength of the strong interaction is in this range. It's about 10, let's say. Then the electromagnetic interactions are 10 to the minus 2, which is 1 over 100. So it's 100th um, of the strong interaction. The weak interactions are a factor 1,000 down, so compared to the electromagnetic interaction, so rather weak. The gravitational interactions are down to a factor of 10 to the minus 39. That is a very small number. That's 0.00. You have 39 zeros and a 1. Okay, it's that tiny a number. So since the gravitational interactions in the microscopic realm are so weak, one can very safely neglect gravitational interactions and worry about just the strong electromagnetic and weak interactions. Okay, Anuradha, you have to tell me when I have to stop. I'll stop at whatever time you tell me. Sorry, there was no one to take that. Anyway, let me continue. Yeah.
Yes, sir.
Sorry, who's talking?
No. I'm Ritvika, sir. Anything you wanted to tell me?
No, that's why I'm saying that, I'm going really slow. I've already lost a lot of time. So how long can I go for? Or just
So you carry on. It's okay.
Just go on till people disappear from the scene. Anyway, I'm not sure whether I'm talking only to myself or not. But
no, sir. Actually, people are willing to ask questions to you also. But I have said that after your talk, the session will be open for discussions. So if you want to take questions in between, we can open it. But I think it would be better if if the questions are taken after the talk.
I think I'll wait till I finish to take
yes,
questions.
sir, please.
Let me.
Yeah, please carry on.
Okay, so to understand this world of elementary particles, the framework that we need is called quantum field theory. What is quantum field theory? As I told you, there were two revolutions that happened in early 20th century physics, that is quantum mechanics and special relativity. Quantum field theory actually brings these two together. And in bringing these two together, um, there are some um, huge complications. It actually becomes quite difficult to work with this um, theory. So initially, it took a lot of time to really understand how quantum field theory works. But people have now had experience of this for the last 70 or 80 years. The dust is settled and we can do really precision calculations with it, as I'll show you in the next few slides. Okay. But two important things you need to remember about quantum field theory, because when you bring quantum mechanics and relativity together, there are two things that happen. One is that you have what are called antiparticles. So we had an electron, for example, and the electron is negatively charged. And quantum field theory tells you that there will be a partner for the antiparticle for the electron, which is called the positron, which is exactly like the electron. It has the same mass as the electron, but it will be positively charged. So in fact, when you bring an electron and a positron together, it will just disappear into energy. They have exactly the opposite attributes. It's anti um, attributes, and they will just annihilate each other. Okay. And there's also, so each particle that you have, the proton, the neutron, so all, or at least in terms of the quarks, if you talk of the quarks and the leptons that I talked about, each of them has an antiparticle. And also because you have combined quantum mechanics and relativity, that is combined two very weird things together, weird things start happening. Now you can actually produce what are called virtual particles. Virtual does not mean Zoom meetings here. Virtual means actually particles that are not constrained by energy momentum conservation, that you can actually make much heavier or more energetic particles in the middle with, rather you can violate energy conservation for very small times, because this is allowed by what I talked of as the uncertainty principle. Okay. So these virtual particles come um, inside in elementary particle interactions, and you will not be able to. So these are not real particles, and but they actually complicate the whole picture of whole picture in quantum field theory. Okay. Now, when you're looking at something so complicated, you need something to hold on to, and what you really hold on to here is are symmetries. Okay. So you look, so basically, um, symmetries give you an understanding of what the system is. So if I know, for example, that no matter how I look at the system, at what, if I have an object, if I look at that object from any direction whatsoever, and it looks the same, then I know that it has what I would call a rotational symmetry. Yeah. So once I have a symmetry, then there is a fundamental theorem due to a famous German mathematician called Emmy Noether. She came up with this theorem in the early 20th century, which said that if I have a symmetry, then I will have certain quantities conserved. So things like conservation of energy or conservation of momentum, which I can actually measure in experiments, are indications of some symmetries. So I so if I take these elementary particles, I do an experiment with them, I find certain conserved quantities, I can infer what symmetries are there. Or I can do the other way around. I can go and make a theory, build it up on symmetries, predict such and such conservation laws would exist, and actually check in experiments whether that is done. Okay. So one fundamental symmetry that we always have in all our quantum field theory calculations is Lorentz symmetry. And by Lorentz symmetry, it just means the symmetry of relativity. It is like rotations, but rotations in a generalized space. It's not the three-dimensional space where we normally visualize rotations, but rotations in space-time, because time becomes the fourth coordinate in relativity. Okay. Other than these, there are symmetries related to what are called discrete symmetries, which are symmetries related to space reflection or time reflection. So if I were to take a system and look at it, gets its reflected image in space, which means I look at it in a mirror, does the system look the same or does it look different? Okay. So space reflection is normally called parity, which is denoted by P here, and time reversal is called T, and charge conjugation. So flipping the sign of charge, which is called C. And again, within quantum field theory, a very fundamental theorem is proved that if you take the combined operations of all these three, that always has to be valid, which means you can violate, in a theory, you can violate one of these symmetries, but you cannot violate a combination of all three. All three have to be conserved together. Okay. Other than this, there is another kind of symmetry, which is to do with the fact that you have conservation of charge, and that is called gauge symmetries. And this is the gauge symmetry that is going to be very important in guiding us through making theories of the electromagnetic interactions, the weak interactions, and the strong interactions. Okay. So let's start with the electromagnetic interaction. So what you'll ask me now is, why are we worried about electromagnetic interaction? Because this was already taken care of by Maxwell. Indeed it was, but what Maxwell had done was what we now call a classical theory, okay, which is not, by which I mean it's not a quantum theory. So I want to take Maxwell's theory and make it quantum. Okay. So how do I do that? I make a quantum field theory which is consistent with all the symmetries of Maxwell's theory. And then this theory that I arrive at is called quantum electrodynamics. And this is the quantum theory of electromagnetic interactions. So if I take charged particles like electrons and I look at their interactions, then I can describe it in this theory. And these interactions are mediated, as I told you, by photons. Okay. Photons are particles of light, and by particles, I mean something a little different now, but I'll reserve this for the question and answer session because I don't have time to go through it right now. Okay. But take it from me that these charged particles are interacting by exchanging photons. Okay. I don't know what's going on here. Strange things are happening on this. Anyway. Now the thing is, how strongly does the photon couple to these charged particles? And that I told you already is given by, as I said here, that is a factor of 1 over 100. Okay. The c square of 4 pi h bar c is 1 over 137. This is the quantity that measures how strongly the electrons couple to the photon. Okay. This is a small number. It's 1 in 100, okay, which is nice because if I have one photon coupling to an electron, then I get a factor of 1 over 100. The price I pay for coupling the second photon to it will be another factor of 1 over 100 and so on. So I can do this in terms of this systematic expansion, which in physics is called a perturbation expansion, where I start originally with a coupling of just one photon. And then at next level, I would have 2 photons, and next I would have 3 photons and so on. And then see how this will work, because that will be a simpler way of going through something as complicated as this field theory. So here I have a picture. This picture is called a Feynman diagram. Originally, Feynman was the person who thought of working with diagrams of this kind. and makes for very, very good calculational simplicity. So here we are talking of an electron and a positron, okay, scattering of each other and producing a muon and a positive muon, its antiparticle. And this is happening through the exchange of this. So this wiggly line that you have here is a photon. These lines here are the electron and positron lines. These lines here are the muon lines. And the wiggly line here is the photon that is exchanged between these. Now we start by making the assumption that it is just one photon that is being exchanged. And so you have a price of 1 over 100 here and a price of 1 over 100 here paid, but that is the leading term in this whole thing. Now you can ask, does this describe this whole scattering process? Obviously the answer is no. So what would happen if you have, instead of one such photon, you had two photons? Suppose you had two photons, like you have one photon here and then one more photon which is being radiated from here. What would the consequence of that be? As I said, because you have to couple this photon here to the electron and you pay a price of 1 over 100 for that, it means that this is going to be 1/100th of this. So this is going to be negligible compared to the original, compared to this diagram. Sorry, was someone saying something? Okay. So this kind of diagrams are going to be much smaller in comparison. Okay. And so we can just work with this diagram and try to do the calculation in field theory with such a diagram and see what the answer is. And it turns out that the answer is quite pretty. So this is exactly this process that E plus C minus, electron positron going to two muons, which has been measured in different experiments. So this is a graph from the experiment. These dots that you see here are the various experimental data points. And this curve that you see here is the result of this calculating this diagram. And the theoretical calculation agrees quite well with these various dots, with these experimental points, which means that
Uh,
sorry, what is this disturbance? I can't
yeah,
understand.
please mute your mics. This is a request to the audience. Please keep your mic in mute.
So one would have thought that this is very nice. We did a simple calculation of some diagram like this, and that can give this kind of neat agreement with experimental results. So we should be able to do this quite easily. Turns out that this is not true. In fact, you could also have diagrams of this kind where these wiggly lines are again photons. If you were to combine, take the photon and loop it back on the electron and make loops of this kind, or loops of this kind, or make loops out of electrons, then these loops actually start messing up your calculation. And in fact, because of the existence of, as I told you, virtual particles, the amount of these virtual particles are not constrained, as I told you, by any conservation laws. So the amount of momenta that can be running through these loops, or amount of energy that can be passing through these loops, can be as large as you want. And because of this, the contribution of all these diagrams becomes infinite, which is ridiculous, because you would have thought that these diagrams would be even smaller, but they turn out to be infinite. So this was actually a major problem in the late 30s and early 40s, when people started doing these calculations. And it was the combined efforts of three physicists, Feynman, Schwinger, and Tomonaga, which where they realized that we were doing it all the wrong way, that in fact, what you need to do is a process of what is called renormalization. What is renormalization? Renormalization is a way by which you can redefine terms in your theory and also cancel the infinities in your theory so that your answers are finally finite. Okay. When is that possible? That is possible only when you have a gauge symmetry, like you do in electromagnetism. And because of the existence of the symmetry, you have renormalizability. So it's all tied up in a way because um, we know that electromagnetism has infinite range of interaction. That is, which means basically if you take two electric charges and move them away very far from each other, there is still an interaction left over. They are very large range interactions, infinite range. And the infinite range of interactions means that the particle that is exchanged in these interactions, this particle, the photon, that is massless. And because of that photon being massless, the range being infinite, you have what is called gauge symmetry. These things are all equivalent terms, and that makes your theory renormalizable, which means that in this theory, it is possible to get rid of all the messy infinities and get um, finite answers for the observables that you calculate. Now, when this was actually originally proposed, as you can imagine, when I am saying this, you may also be wondering, what am I saying? That you first get infinities and then you brush away the infinities, somehow you cancel them, and then you get an answer. But this is actually a very well-defined procedure, and it is now very well understood, and we can do neat calculations in such renormalizable theories. So there is a class of field theories where we can do such good calculations, and those are what we call renormalizable theories. And uh, this renormalizability makes actually quantum electrodynamics, the theory of electromagnetism, the best tested theory we have. So it becomes a prototype for all other field theories that we may want to discuss. And just to sharpen that claim, let me show you. There is some quantity, don't worry about what it is. It's called the electron anomalous magnetic moment. And it is one of the classic predictions of this theory. I just wanted to show you the numbers, what is calculated in theory now. This was originally calculated in 1948 by Julian Schwinger. After that, this calculation has been improved to 5 orders. And the more this theory number that I'm showing you is from a calculation done as late as 2010. The experimental measurement is as late as 2015. And you can see that the agreement between theory and experiment is not good, it is spectacular. It is an agreement to more than 10 decimal places. Okay, you see that there is a 10 raised to minus 12, which means it's 0.000 various things. And all the significant digits are agreeing between. So this is in fact the best agreement between theory and experiment in the history of all science. It's quite a big statement. So let me very quickly tell you then how from here we go to understanding strong interactions and weak interactions. The problem with strong and weak interactions is that they are all, um, you know, they are all operative only within the size of the nucleus. So they're operative over a very small domain. So the range of the interaction is very tiny. Okay. On the other hand, I told you that when I want a theory which is renormalizable, I need a gauge theory, then the range of the interaction has to be infinite. Okay. So this seems to be at variance with what we want. And the other problem with strong interaction is that um, the strength of the interaction is very, very large. Okay, so go back to this slide where I showed the different strengths of interactions. Strong interaction is in the range of 1 to 10, whereas electromagnetic interaction is 1 over 100. That 1 over 100 helped us organize that perturbation expansion, which we showed. So it was possible to, what does that mean? That means that we could ignore all the more complicated um, contributions from those diagrams because of the fact that this strength of the coupling is 1 over 100. The strength of the strong coupling, however, is 1 over 10. So if 1 between 1 and 10. If I were to try to do this kind of expansion in strong interactions, then it won't be valid. So basically, it means that strong interactions are too strong, and how are we going to address this issue uh, within strong interactions? So can we, just as we did a theory of electrons or muons interacting with each other through exchanging photons, can we make a theory of quarks interacting with each other through exchanging some particles, which we'll call gluons? So is such a theory possible? It turns out dramatically that it is in fact possible. Because what happens is the symmetry of strong interactions turns out to be much bigger than that of electromagnetic interactions. It's very similar, it's a gauge symmetry, but it's very much bigger. Because it's bigger, the mathematics of it works in such a way that this coupling that I was talking about, which is between 1 and 10, this coupling that I was talking about, normally these are called coupling constants in physics. Turns out this coupling is not constant at all. This coupling, in fact, varies with energy. In fact, it varies with energy in QED also, but it varies very little, and it's not relevant. But in um, the theory of strong interaction, which is analogous to QED, it's called QCD, it's called quantum chromodynamics instead of quantum electrodynamics. In QCD, this coupling actually becomes small as you increase this energy, which is, and just go to, so these are energies which are being measured in some electron volt units. This is a typical unit that is being used in high energy physics, which, so this is in between 1 GeV, which at 1 GeV roughly it is about, the strong coupling is about 1. And by the time you go to 100 GeV in energy, it has come down to something like 0.1. Okay. So the coupling constant of coupling of strong interactions goes down very quickly with energy. And you can see these all these data points here agree superbly with this curve, which is the theoretical curve. And it tells you that, in fact, if you go to the high energy region, then you should be able to actually work again with that kind of perturbation expansion, should be able to work with it in exactly the same way as we did in QCD. Then you will ask, oh, but how will we work with it in QCD? Because the range is not infinite here. The range is very finite. It's only within the nucleus. The answer again is to do with the strong coupling. Because of the strong coupling, the protons and neutrons and the entire interaction is confined inside the nucleus. If it were not for the strength of the coupling, it would not be so. If that is the case, then if we go to high energies, we may be able to do something analogous to what we did in electrodynamics. And that's what we do in experiments now. For example, we take two protons here. These are two lines showing two protons. This, what happens when you scatter two protons at high energies is that you pull out from one of them, you could pull out, let's say, one quark, and you could pull out a gluon from the other. So these elementary degrees of freedom start mattering at very high energies because of the fact that your coupling constant has now reduced to a small amount. Okay. And the scattering process goes through in what is usually called a hard scattering process, and very much similar to what happens in quantum electrodynamics. But as these objects are produced, this quark and a gluon is produced here, and it flies off, it degrades in energy. So by the time it reaches your detector, it has degraded in energy, and in that process, it gets confined and bound into the known particles again. It becomes particles like the pions or so on. And so what you get instead of, you don't ever see a quark or a gluon. This problem is called the problem of quark confinement. You don't ever see a quark or a gluon because of the strong interactions. You always see the composites made out of these quarks and gluons. So what you would see, in fact, is a jet of particles coming in this direction and a jet of particles coming in this direction. And that you will infer that a scattering of the elementary degrees of freedom actually happen. Sounds extremely complicated when you compare it to quantum electrodynamics. So you'd wonder, do these actually make sense at all? Do they compare well with the experiment? And I'll just leave you with a recent figure of the production of these jets and the comparison with data. And you see in this picture, there are 1, 2, 3, 6 curves, and they are for different regions. And in these different regions, you have all these data points. You can see these dots. These are all the data points, and the red curve running through it is the theory. The theory matches beautifully with experiment. Okay. So we have not only figured out the theory of strong interactions, but we are actually now able to do very precise calculations in spite of all these complications that come up in discussing it. Finally, I think I'm going to go through weak interactions very briefly and then stop. I had hoped to do a little more than that, but I just want you to have an understanding of weak interactions, and then I'll stop. And if you want, we can discuss some more in the question answers, if you still have the patience for it. So as I said, we have a theory of electromagnetic interactions called quantum electrodynamics, and QCD, quantum chromodynamics for the strong interactions. Now, the only other interaction we need to understand is weak interactions, because gravitational interactions, we said we'll ignore because they were just too weak. It did not make any sense talking about gravitation at this stage. Yeah. The problem with weak interactions is again that they are very short range. They are only nuclear range. And you cannot even hide behind the fact that in the strong interaction case, we said they were short range because of the strength of the interaction, that it was very strong interaction. So it was confining the interaction within nuclear range. Here it is it's weak, much weaker than even electromagnetic interaction. And why would it be only of nuclear range? Why is it not? Why is the range not infinite? As I said here, the range of interaction and the mass of the object which is carrying the interaction, they are tied together. So when the range of interaction is infinite, the mass of the object carrying the interaction is 0. But if the range of the interaction is very small, finite, then the mass of the interaction is actually large. Okay. So you can do a very quick calculation to infer what the masses of these objects could be. And it turns out these are masses in the range of 100 GeV. Okay. If you don't understand the unit GeV, just take it as a number. It's indicative of some energy. Okay. And there are 3 such kinds of particles in weak interactions. Unlike photons and gluons, here you have, because in the original weak interactions, the charges could change in different ways. So you have 2 charges, charged nuclear interactions, and 1 neutral interaction. So they're called, these exchange particles are called W plus, W minus. There is a positively charged W, negatively charged W, and Z. So W plus, W minus, and Z. These are just names given to these 3 kinds of particles which mediate the weak interactions. And these W plus, W minus, Z play the role of photons in quantum electrodynamics. Now the problem, however, is these are massive. And because these are massive, the theory is not a gauge theory anymore. You don't have a gauge theory. And because it's not a gauge theory, it's not renormalizable, which means calculations done in this theory will not make sense. So what is the solution to that? Solution to that is, technically speaking, this thing is called that symmetry must be spontaneously broken. I will come to spontaneous breaking of symmetry, but before that, I would, okay, let me show you the slide to the spontaneous symmetry breaking. This is a typical picture that is shown in the context of spontaneous symmetry breaking and what is now called the Higgs mechanism. And this picture is very just imagine that there is a small ball, and this is a Mexican hat. So these are typically called Mexican hat potentials. So the idea is that if you have something with a ball which is sitting right here in the center, then it is seeing a very symmetric object around it. It's seeing completely a spherical rotation symmetry around this. Okay, but right where it is sitting here, this ball is unstable. It is bound to roll over because it's a point of unstable equilibrium. Just a little push and it will roll down, and it will roll down and come to the base here. In the base, it can choose any one of these positions around the circle and the base. And once it has chosen that position, the symmetry is no longer there because you have chosen one direction in that along that circle. So that circular symmetry is no longer there. Okay. This is basically the idea of gauge symmetry, that this lower energy configuration, which is called the ground state, which is where the system prefers to roll down to, is what the system will prefer to go to because it's a lower energy thing. But that does not have the symmetry of the system. The system has a symmetry. It has a spherical symmetry. And if you are sitting here, you would have seen it. You would have seen the rotational symmetry if you were sitting here. But because the system rolls down here because of energetics, it is not seeing that symmetry. And if you could roll down here, it could roll down anywhere here. So you have a whole lot of equivalent points, all points on this circle along which this ball could have been. And that being along these points of a circle means that you can move around anywhere around this without the expending of any energy. It's all equivalent. That corresponds to something which is a massless particle. Okay. But so basically, people realized very early that it is possible to um, do this for gauge symmetry case also, break the symmetry and break the symmetry spontaneously in this fashion. And but the price for that would always be that there will be a massless particle associated with it. Okay. This particle was called a Goldstone particle. It created a lot of confusion for a while because people said that if you try to break gauge symmetry in this way, you will always be stuck with a massless particle. And we never see such a massless particle in nature. So this whole thing must be wrong. Till Professor Higgs stepped in and he redid this calculation in a clever way, which details I cannot go into right now. And but he again used the fact that there's a gauge interaction here to actually get around this problem. And instead of this particle being massless, he made it acquire a mass. So in the process, what you do, so you, by doing what is called the Higgs mechanism, you basically have the cake and eat it too. You have a finite interaction, you have massive exchange particles which are mediating the interaction, but you still have gauge symmetry. It's called spontaneously broken, but spontaneous breaking is not the breaking of symmetry. The symmetry is still there, but it has been hidden. It has been hidden in a way where you keep all the benefits of the symmetry, but you still give masses to the exchange particles. And you do all this at the price of bringing in a new particle, which is called the Higgs particle. The Higgs particle is has some mass. And of course, then because it is a massive particle, it requires some time to go and search for it. Its interactions are very, very feeble. So it's not at all easy to detect. So between the time the prediction for the Higgs was made and the time that it was eventually detected at the Large Hadron Collider in CERN in Geneva, it took more than 50 years. So this is a picture of the facility in Geneva. This is not inside. In fact, you see this huge circle here, and that circle is kind of indicative of the accelerate tunnel that runs around here, The particles, the protons which are scattered in this experiment are accelerated here. This tunnel is underground, deep underground, and it is 27 kilometers in circumference. The dotted line that you see here is the national border between Switzerland and France. So these protons make several transits, several million transits between Switzerland and France every minute. And it is in this experiment at the Hadron Collider, this 27-kilometer ring, that the search for the Higgs boson was done at the maximum kind of energies that we have ever attained. This Higgs was eventually found in 2012. This is a picture of that event. And actually, I can show you also a plot. The Higgs what they do is to look for the decay of when the Higgs is produced, they look for its decay. It's a very tiny decay into 2 photons. And they look at what is called the invariant mass of the 2 photons. And there you see this bump here at something like 125 GeV. And that is the Higgs particle. Okay. So, yes, so I'll kind of, so basically with the Higgs, most of the edifice of the standard model gets completed. And one can say now we have the full story. I just wanted to talk a little more about that, but for want of time, I'll stop here and take questions and just leave you to look at this last slide. And I want to basically indicate that, we are always hasty to conclude in science. We want to always say in conclusion, that's how we wrote our journals in the labs. And we are also now very hasty in concluding that the standard model is complete and that we have to go and look for structures beyond the standard model. But I think we have to appreciate that even within the standard model, there are many issues still to be addressed, still to be understood. And so I'll leave you to look at that slide. And if there are any questions, I'm happy to take them.
Thank you, sir. We will open the session for question, answer, and discussions now. I would request the audience to raise their hands so that I can call them one by one and they can unmute themselves and speak. Or they can also write in chat.
So let me ask Professor Sridhar, what do you see? Where do you see particle physics going from now onwards? Because we have come to an end, and we are looking for new things. Nothing is being seen. So where do you see particle physics going from now onwards?
Thanks for asking this question. Okay, so I'll go back to sharing screen. So as I was saying, even within the standard model, there are several issues to be tackled. And a lot of things need to be done even here. And so there are issues also beyond the standard model. So beyond what we understood as electromagnetism or strong interactions or weak interactions. Because even when you look at the structure of this, there are issues which point inward and they point beyond. And some of the solutions may exist not within the purview of the standard model, but beyond it. Okay, so there are a lot of such issues. And there seems to be an anxiety about, oh, after the Higgs, we have not had any new discovery so far in particle physics. And so where is this all going? And that is a somewhat misplaced kind of anxiety, I feel, simply because that we may have chosen to think of many of these issues beyond the standard model in rather simplistic ways. And they may actually wait for much higher energies to be, we need probably much higher energies to explore these theories very properly. And those kind of experiments are not very far in the future, I think. I mean, I'm being a bit optimistic here, but there are plans for the future circular collider, 100-kilometer circumference. This is the 27-kilometer circumference of LHC. They're planning this big 100-kilometer circumference collider where the particles will be accelerated to 100 TeV, which is 7 times the highest energy that LHC will be reaching. And at those kind of energies, definitely we will be able to answer several of these questions. And I think that it is a bit premature to say that we have already explored it, there's nothing more to be done. I think there is a lot that the future will be discovering.
Any more questions? Okay, Faisal asked me. Please unmute yourself and ask.
Yeah, can you hear me?
Yes.
Hello, Professor. Thank you so much for this very lucid lecture. And I'm a physics teacher, who sort of reads physics on an amateur basis. And physics always, we had an element of faith in it. Like in economics, etc., there's always this dispute about this theory or that theory. And of late, at the highest level in physics, with people like Smolin and Penrose, you hear reservations about what is happening in string theory and we are being misled and so on and so forth. What would be your take on all of this?
Sorry, can you repeat that last line again?
No, I said at the very highest level of theory, you hear people like, say, Roger Penrose and Lee Smolin, etc., express reservation about this whole culture of string theory and this intensive mathematics which is happening without any kind of experimental basis. So I wondered what would be the substance to those arguments and what would be your take on it?
Faisal, I had wanted to talk about all this at length today.
Right.
But anyway,
not a problem.
Answer you briefly. See, okay, I don't know. I may have not conveyed it in my talk as well as I wanted to, but what I'm trying to emphasize is that there is one which is one activity in this kind of fundamental physics, which is about developing new theoretical pictures, right? Theoretical speculation is a very, very important part of, and theory is actually moving very fast compared to what experiments can achieve because we are limited by technology and other things. Okay. But eventually, only experiment can be the arbiter of what is true and what is not true. Neither Penrose nor Smolin nor anyone can tell us that. What happens, and you're referring to string theory, but it's common to not just string theory, but to all theories of quantum gravity. And we go back to my slide here. I said I can ignore gravitational interactions, right? Because gravitational interactions are so weak. The question is, when do gravitational interactions matter? When do they become strong? They become strong at very, very high energies. At energy scales which are about 10 raised to 15 or 16 times what is available at the LHC. Okay. So at these very high energies, you will be um, able to actually test features of quantum gravity. And of course, you cannot use conventional accelerator technology to build that kind of an experiment, which is not to say that you may not have new technologies which will not help you conceive of new kinds of experiments. But as of now, there is no conceivable way. I'm not even saying there's no experiment. There's no conceivable way of testing any theory of quantum gravity. Okay. So it is like two theologians fighting over which interpretation of a holy text they are happy with, because there is nothing which will decide between the two. Of course, just like in holy text, there may be a lot of beauty in the kind of theories that we create. I personally think string theory is a very beautiful thing, but there are also very beautiful things about theories that compete with string theory. Okay. There is elegance in their formulation. There's beautiful mathematics to be obtained from them, and so on. But as far as physical theories go, they need to be tested. And unfortunately, we can't test any of these. So that's where we are.
Thank you.
So, any more questions? You can raise
Hello.
your hand. Yes.
Huh. Yeah. So Sridhar, as usual, you have been giving a good presentation. Of course, I've been coming in and out, but I don't know. I think what I wanted to ask, as you said, since you came to the experimentation, so I just wanted to ask, like, we have so many accelerators coming up and so on. So where do you think we stand? I mean, the synchronization with experiment versus theory. Maybe I missed it, but I just wanted to pose this question.
How do you mean synchronization?
I mean, are we in sync? Sometimes there is always a time lag. The theory comes first and then you do experiments to prove it, or vice versa. And sometimes the time gap is quite long.
So there are
So,
certain kind of questions, as I just said, we don't even
huh,
know how to go about
huh,
thinking of an experimental test. There are certain ones we know how to go about them, but we probably will have to wait 50 years to get an experiment actually going.
yeah,
There are other situations, even within fundamental physics, where you have a lot of data already available, but there is no theorist who's analyzing them because the calculational tools to do those theories don't exist, or the computers needed to do those theoretical
huh,
calculations don't exist, or so there are all kinds of situations. So
huh.
it's not a simple thing about saying that I have an experiment and I
Mhm.
have a theory and how do they
Yeah,
match.
yeah. Thanks.
Mhm.
So, anybody else who wants to put a question to our speaker today or discuss?
Okay, I guess there are.
I don't think anybody else has raised hand. So so let us then thank the speaker today. Mishra, madam, would you like to have any concluding remarks? Give any concluding remarks?
I just want to thank Professor Sridhar for such a simple description of a vast body of knowledge that the particle physicists have acquired over so many years, hundreds of years. It was really very rather complete description. And for the students, particle physics has been a strength of the department for now. We can see from how long some of our best students have been from the particle physics and nuclear physics option. And Professor Sridhar has been involved with the department later also, which I mentioned briefly. He's very fond of teaching, and he has been teaching this part of this particle physics course. He has taught to several batches, and he has also guided a student along at Bombay University. He has also taught at refresher courses in the department. And anybody who is who could not today ask because of some time constraint, you are all encouraged to approach him and ask your questions and take inspiration from him. And you can see from how far you can reach starting from UDP. So I think the purpose of GYAN is being served very well. And we look forward to all your presence and more encouragement from the participants. Thank you very much.
Thank you.
Thank you, Sridhar.
Thanks, Sridhar. Thank you.
Thank you, madam. I'd just like to inform that the talk is on YouTube. So if anybody has missed any portion due to the technical problems, you can go to YouTube and see this talk. So now it's my pleasure to propose a vote of thanks. So firstly, I would like to thank the university authorities for allowing and helping us and supporting us through all the lectures of the GYAN series, and UCC for the technical support. All the alumni who are here, the illustrious alumni, our past and present faculty and students, my colleagues, particularly our HOD, Professor Anuradha Mishra, our non-teaching staff, and definitely last but not the least, today's speaker, Professor K. Sridhar, for giving us his valuable time. It was a wonderful talk, as Madam said, and I'm sure there would have been a lot of more questions. We had some technical glitches today, but the talk is available on YouTube, so please go and see it there. And I think Sir will also be there to answer your questions. I think you can contact him otherwise personally also. So thank you very much, Sir, again for being here today with us. And I would wish all of you a very good evening, and we will conclude the session here. Thank you.
Thank you.
Thank you.